Howdy, my name is Mingi Yo. I'm a master's student studying under Dr. Palermo, and my defense work is over a design of a wideband low noise amplifier and a CMOS FinFET technology. So when I first started learning about the topic, I asked myself, what is a low noise amplifier? Here on the diagram above, I've shown a typical super heterodyne RF receiver block diagram. The LNA is highlighted in red up here. It is positioned directly after the antenna, and its function is to amplify the tiny signals obtained by the antenna without adding much noise to it. This amplification stage is necessary because components down the line, such as the down conversion mixer and then the variable gain amplifier, tends to add a lot of noise to the signal. By boosting the signal strength early on, we are able to maintain good signal to noise ratio in front of the demodulator, the ADC in this case. And so the key takeaway point is that the LNA helps the RF receiver process very tiny signals that are mixed in with that are very close to the noise floor. Here on this table, we list out the typical usage of wireless frequency throughout the spectrum. At the lower end, we find underwater and underground communication, where the long wavelengths allow for super long distance communication, but due to the relatively large size of these antennas, it's not suitable for consumer usages. At the low frequencies and medium frequencies, we find AM, long range radio broadcasting. And at high frequency, we find amateur radio bands where licensed enthusiasts can talk with other licensed enthusiasts within the area. At very high frequencies, we find FM radios, which we typically listen into in our cars. At ultra high frequencies, we find 4G cellular radios and wireless LANs like Wi-Fi to allow for wireless internet connectivity. And at the highest frequencies, we find point-to-point microwave systems such as the modern 5G communication. And our work in this defense covers it works within these high frequency and extremely high frequency bands. So why wideband LNA? Modern technologies like cloud services are data hungry, and we need ways to keep up with the demand. To increase data throughput, one of the methods is by widening the bandwidth of the LNA. This is and listening on multiple channels at once. This is like watching the news while enjoying a TV series. So wideband LNA can tap into more information simultaneously. Furthermore, the 5G new radio in the second frequency range operates at above 24 gigahertz. And in the last 5 years, USA, Europe, and Asia are slowly expanding the upper end of the bandwidth further and further into the V band. And we would like to create an LNA that can target the second frequency range of 5G, so from 24 gigahertz out to the 70 gigahertz. Now that we have introduced the low noise amplifier, next section will dive into a background information of a CMOS low noise amplifier design, while this section primarily focuses on narrowband LNA designs. Most of the information here is applicable to wideband LNA designs as well. Then the proposed work will be shared by starting with some literature survey, and then the RF characteristics of a FinFET technology will be highlighted. Then the architecture of my proposed LNA will be shared. And then the dual resonance techniques which are employed in my design to extend the bandwidth of our LNA will be explained more in detail. And then the measurement results will be shared and compared against the state-of-the-art designs to finally conclude the presentation. Noise figure is one of the performance metrics of a LNA. How it works is that when we have these input signal power like so with some noise mixed into it, as these signal power and input noise power is fed into the LNA, at the output we get an amplified version of the input signal and a amplified version of the noise. Plus, it creeps up a little more because the LNA adds its own noise on top of the amplified noise. What noise figure does is it measures the degradation of the signal to noise ratio that we have from the input to the output. And then the equation for noise figure is given below, where NF is equal to 10 log 10 SNR in over SNR out. So for example, if the input SNR is 10 dBs and then the output SNR is 6 dBs, and then the noise figure will be 10 dB minus 6 dB, 4 dB. Lower noise figure indicates better performance, which means that LNA does not add as much noise onto the input signal that it amplifies. There are two primary noise sources in an LNA. First, any unwanted resistance in series with the input of the LNA adds a white thermal noise to the input, which degrades the noise figure of LNA. Second, noise source comes from the device itself. The plot to the right shows the noise spectrum of a FinFET device. At the lower frequencies, the flicker noise is dominant, and after some corner frequency, a thermal noise will be more dominant. At the millimeter wave frequency range that we are working with, uh, we are far into this thermal noise region, and then we only typically consider the thermal noise effect from the device. For high frequency circuits, we use scattering parameters, also known as S parameters, to characterize how electrical signals behave within a network. It describes how electrical signals are transmitted, reflected, and/or amplified when in front of impedance discontinuities or impedance mismatches, or active sources like transistors. For a two-port network, there are four S parameters. S11 measures how closely the input impedance matches to the source impedance. Likewise, S22 measures how closely the output impedance matches to the load impedance. S21 measures how much of the input signal is amplified to the output. And S12 measures how much of the output signal is rejected from traveling back to the input. These four S parameters will be talked about more in detail in the upcoming slides. Starting off with the S11, I've given out the input reflection coefficient equation up top, the gamma in, and gamma in is equal to S11 plus the second term, under the condition that the load is perfectly matched, so when gamma L is 0, the second term goes away, such that S11 is any reflection at the input is solely due to the impedance mismatch that we have at the input. And then this last term tells us that S11 is best optimized when Zn, the input impedance of the network, is when Zn is matched to Rs, and Rs is typically 50 ohms. But the question here is that a input impedance of a transistor is usually capacitive. How can we mimic a 50 ohm resistor? One of the most popular technique is by placing an inductor at the source of the transistor. This is called an inductor degeneration technique. And what it does is that when we find the input impedance equation looking in from the input, we arrive at this following equation down here, where the Laplace variable S is equal to J times 2 times pi times frequency. So the terms that contains S's are imaginary and also frequency dependent. This last term over here is not frequency dependent and also is real. So the parameters such as the transconductance GM and then the source inductance LS1 can be chosen to equal to 50 ohms. Then with the rest of the imaginary terms, you can tune it such that it equals 0 at some resonant frequency. So by using inductor degeneration, we can create an equivalent input network that mimics 50 ohms at some resonant frequency. Likewise, S22 is related to the output reflection coefficient gamma out, and the equation for gamma out is listed up top. Under the condition that the source is perfectly matched, so when gamma S is equal to 0, we don't need to consider the second term. Then what S22 then means is any reflection at the output is solely due to the impedance mismatch that we have at the output between the load and the output impedance. And this last term again suggests that S22 is best optimized when the output impedance is equal to the load impedance, RL. Typically, for the blocks in the RF receiver that succeeds the LNA, such as the mixer, VGA, they are typically built on the same die, such that the matching requirements in between these internal interfaces are more relaxed. Instead of focusing on maximizing the power delivery, people tend to focus more on maximizing the voltage swing at these internal nodes. S21 is a network parameter that describes the forward transmission of the signals that we have from input to the output. I've listed the transducer gain equations to the left here, where with the unilateral transducer gain up top and then the zero reflection transducer gain on the bottom. I put it here just to show that S21 is strongly linked to the power gain equations. So to find S21, we just need to look for the gain of the LNA. The schematic of a simple narrowband LNA is shown in the middle here with the inductors LG and LS for input matching. To find the gain of this simply find the gain of this LNA, we just consider the transconductance of the device multiplied by the output impedance that we have. The output impedance consists of a drain inductor LD and parasitic capacitance C1 arising from the device and interconnects and parasitic resistance arising from the output impedance of the transistor and also just the lossy inductor that we have from LD, drain inductor. The RLC tank network captured at the output node is resonant and its frequency profile is shown on the plot to the right. The output impedance peaks at some resonant frequency given by LD and C1. And since the gain is just the transconductance of the transistor multiplied by this output impedance, the profile of the S21 will show some resonant behavior as well. S12 refers to the ability of the LNA to prevent signals from traveling backwards from the output to the input. This is supposed to be a frowny face, but we want high reverse isolation to ensure better stability and to prevent any unwanted coupling between stages. The LNA needs to be stable to function properly. Otherwise, the output of the LNA will oscillate, which would lead to system failures. Once we find the stability is usually evaluated using the Rowlett stability criteria. So once we find the S parameters of our network, we can first solve for the delta factor. And if delta factor is less than 1, we pass the first condition, and then we can solve for the K factor. And if K factor is above 1, then it passes the Rowlett stability criteria. Once K and delta are both met, the LNA is considered unconditionally stable. Input third order intercept point is a measure of the LNA's linearity. So how it works is that when there is two input tones at omega 1 and omega 2, the output spectrum will contain the amplified versions of the input tones at omega 1 and omega 2, and it would generate these intermodulation terms at 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. These intermodulation terms are created due to the nonlinearity in the LNA. And the plot to the right shows how as the power of the input tones are increased, the fundamental tones rises steadily, but the intermodulation term rises much steeper compared to the fundamental. There will be at one point, the power of the intermodulation term will equal to the fundamental, and we call that point the third order intercept point, and then the input power that occurs at the input third order intercept point. Higher IIP3 gives better linearity and it provides lower distortion of the input signal compared to LNAs with lower IIP3. Now that the background information of the simple CMOS low noise amplifier has been talked about, we would like to share our proposed wideband LNA work, starting off with some simple literature survey, and then we will highlight the key RF characteristics of a FinFET technology. Then the schematic of our proposed LNA will be shared. Here in this table, we list out 3 recent examples of state-of-the-art wideband LNAs, and we compare their performances across 5 different performance vectors, which are gain, bandwidth, power consumption, noise figure, and input matching level. Starting off from the left, the red LNA by Kazan achieved very good gain and 100 gigahertz of bandwidth, making it one of the widest in the recent works. But by using a 4-stage differential architecture with high supply voltage, they consumed way too much power relative to other single-ended examples. The blue LNA in the middle by Liang used three-stage single-ended architecture to report much better power consumption than the red LNA. They also obtained good gain and decent bandwidth as well. However, they reported a very important input matching level of -6 dB right in the middle of their bandwidth as well. Lastly, the green LNA by Chen used single-stage, single-ended architecture to report one of the best power consumptions in the reported works, but due to the simplicity of the circuit, they suffer from low gain and narrow bandwidth as well. Furthermore, I like to highlight that the good input matching level of -10 dB is not that impressive because matching a narrower system is much easier than matching these wider band systems. As all these LNAs kind of have suffer in one or more performance areas to get great benefits than others, this begs the question, can we design a competitive state-of-the-art LNA that hits all five performance vectors equally? First, I'd like to highlight the gate resistance of a FinFET device. The figure to the left shows a 3D view of a FinFET device with the drain, source, and gate terminals labeled as such. The channel, the fins, exist perpendicular to the gate. And to analyze for the gate resistance, we take a cross-sectional view across this red plane over here. To arrive at this figure to the right, where the green material is the gate material, the poly, yellow is the silicon oxide, and then the fins are in blue. The FinFET device, the gate resistance for a FinFET device consists of vertical resistance components and horizontal components. But no lower number of fins, we have less vertical components in parallel, so the vertical gate resistance will be dominated. But at higher number of fins and lower number of fingers, more vertical components will be put in parallel such that the effect of the vertical gate resistance is decreased. But by doing so, it places horizontal resistances in series, such that at the high number of fins and lower number of fingers, the horizontal gate resistance will be dominant. So when designing, we need to consider the trade-offs between choosing a right number of fins and also versus number of fingers. The figure to the left shows the metal stack-up of the FinFET technology. It consists of 11 metal layers vertically spaced out like so, and it is built on a standard silicon substrate of 10 ohms per centimeter. The metal finger capacitor is shown to the right, which is implemented throughout our design, and in the middle we have a 3D layout view of a transistor. Our design philosophy was to route the device terminal straight up to the top metal to reduce any parasitics. The plot to the right characterizes the transistor we have in the middle here. We plotted noise figure minimum in black, transconductance GM in red, transition frequency FT in blue, and maximum oscillation frequency Fmax in magenta. We have decided, and we plotted them against current density. And we have decided to bias our transistor for minimum noise figure at 45 gigahertz, which is the center of our target bandwidth. And this bias point saves 67% of power relative to working at a bias point optimized for peak GM, while providing 76% of maximum GM, 82% of maximum FT, and 96% of maximum Fmax. Here is the schematic of our proposed LNA. We have opted for a three-stage single-ended architecture as it shows a good balance between obtainable gain, bandwidth, and power consumption. And to first explain the techniques that we have used in our schematic, we have used inductive degeneration technique down here, and also resistive feedback technique. By using two input matching techniques, we are able to obtain broadband dual resonant input matching level to extend the bandwidth of our input matching. Moving on to the output of stage 1, we have magnetically coupled the drain inductor LD1 to the third stage's drain inductor LD3. This interstage magnetic coupling provides dual resonant impedance at the output of stage 1 and the outputs of stage 3, which helps to extend the bandwidth of the gain of our LNA. So those were the techniques that we have used in our LNA, and the dual resonance technique that we have used will be explained more in detail in the upcoming slides. First, starting off with the interstage magnetic coupling, we would like to observe a impedance looking into the red node here, the output of stage 1, and also we would like to create an equation that create an equation expressing the output impedance looking into the output of stage 3. To do that, we use an equivalent circuit model, and to explain this equivalent circuit model, the circuit parameters in red here, RCL, maps to the RLC tank that's captured at the output of stage 1, where R represents all the losses at this node due to the inductor, lossy metal of the inductor, the input resistance of the next stage, and the output resistance of the first stage, and C captures the parasitic capacitances arising from the device, and interconnect, and L captures the drain inductor LD1 here. And it is magnetically coupled to this blue circuit parameters, which maps to the RLC tank that we have at the output of stage 3. Finally, the circuit parameters in magenta here represents the overall transconductance that we have from this red node through the second stage transistors and third stages transistor to the blue node. So GM2 captures the cascode transistor of the second stage. The RLC tank here maps to the RLC tank that we have at the output of stage 2. And GM3 captures the transconductance of this cascode transistor of the third stage. The circuit parameters of this equivalent model will be used to express an impedance equation looking into the output of stage 1 and also the output of stage 3. Before we begin, though, we would like to explain our general strategy of identifying a dual resonance. Any impedance equation at steady state simplifies down to the following complex number in the numerator and following complex number in the denominator. This equation can be further simplified by multiplying the top and the bottom by the complex conjugate of the denominator, such that we have just a single complex number, and we group this real terms and just represent it as A for now. We group this imaginary term and represent it as B. Once we find the magnitude of this equation, we see that the magnitude of the impedance rises as A and B terms increases. So if A and B term are maximized at one frequency, then we would have your typical single resonance. But if you are able to maximize A and B at two different frequencies, then we would have two different resonances. And the best way to maximize this A and B terms are actually by minimizing the complex number of the denominator here. This is because the denominator here contains this exponent, and such that when we decrease the complex number of the denominator would decay much faster relative to the numerator. So in general, to create dual resonance, our general strategy will be to minimizing the complex number of the denominator, these color terms, at two separate frequencies. So here up top, we express the impedance equation that we have at the output of stage 1. And on this slide, we are going to examine how the real terms of the denominator are minimized. To simplify the analysis, we consider a frequency-independent GM. Then the real part of the denominator is when the Laplace variable s is replaced with j omega, the even order terms make up the real portion of our denominator, the red, blue, and the green. These color terms can then be combined and set it equal to 0. And once we plug it into the quadratic equation, we are left with 2 negative roots and 2 positive roots. And we're interested in where these roots occur at, so we consider a following special case. So when the inductance of the two coupled resonators are the same, and then the capacitance of the two coupled resonators are the same, and when we assume no loss in the first resonator tank, then F1 and F2 can be simplified down to this beautiful equation where F1 is related to 1 over 2 pi square root L plus the mutual inductance multiplied by the capacitance, and F2 is related to 1 over 2 pi L minus the mutual inductance multiplied by the capacitance. And where M, the mutual inductance, is related to the coupling factor that we have between the inductors. So what this means is that F1 and F2 can be separated out by introducing coupling factor, and they can be pushed further and further away by introducing more and more coupling factor. So in this way, we were able to minimize the real term of our denominator at these two separate frequencies. And on this side, we're going to examine the imaginary terms of the denominator. Again, considering these frequency-independent GM, the odd order terms, which are the turquoise and the magenta, forms the imaginary portion of our denominator. Once we combine them, set them equal to 0, we could take out the like terms first, the j omega, to find one root at the origin, and then we could plug the rest into the quadratic equation to find one negative root and one positive root. The cool thing about this imaginary root, non-zero, non-origin root is directly related to this magenta term, and this magenta term contains the transconductance Gm. So what this implies is that we can control the location of this imaginary root by adjusting the strength of the transconductance that we have. And if you were to place this imaginary root such that it encompasses this F1 real and F2 real, we are able to minimize the overall complex number at these two frequencies. Up top, I again listed the output impedance that we have at the output of the first stage. And on the bottom, I've written out the output impedance equation that we have at the output of the third stage. They are very similar. Although the numerator are slightly different, the denominator of these two equations are exactly the same. And this implies that because the denominator is exactly the same, we would expect the dual resonances to occur at the same frequencies. Now that we have talked about the theory behind the dual resonant impedance, let's see how this actually shows up in our circuit. When I have extracted the output impedance of the first stage in brown here from the cadence schematic, and the output impedance of the third stage in green here, we see that they both resonate at around 30 gigahertz and 62 gigahertz. So this dual resonance in the output impedance will lead to a bandwidth extension of our gain. And then the plot to the right, we show the gain of our LNA without any coupling in red and the gain of our LNA with coupling in blue. And we see that by introducing this magnetic coupling, we are able to extend our 3 dB bandwidth by 26.5%. How can we physically realize this on chip? The coupled inductors LD1 and LD3 are magnetically coupled by bringing their metal traces right next to each other for side-to-side parallel magnetic coupling. But this kind of arrangement sandwiches the second drain inductor in between the two coupled inductors. To mitigate any unwanted coupling to the second stage, we have decided to route the metal traces for the second inductor orthogonal to the third stage's drain inductor, such that the magnetic field vectors are perpendicular and do not affect each other. So far, we've addressed how we extended the bandwidth of our gain. And in this section, we address how the input matching is extended. From our schematic contained two input matching techniques, the resistive feedback technique and inductive degeneration technique. And on the equivalent schematic to the left, we show that the resistive feedback technique can be simplified down to the following RLC notch filter. And then the inductive degeneration technique can be simplified down to the following RLC network. Let's observe where these notches occur at. The blue curve in the plot to the right shows input matching with just inductive degeneration, and it kind of peaks around 60 gigahertz. And when we add resistive feedback on top of that, the resistive feedback technique generates a lower frequency notch around 30 gigahertz to significantly extend the negative 10 dB S11 input matching level. Now, the measurement results will be shared and compared against the state-of-the-art designs. Here above, the picture above, we show the macrograph of our LNA. The core design area takes up 460 micrometer by 300 micrometer of space. To test this chip, the chip has been placed in a cavity on a PCB with the top and bottom DC bias pads wire bonded. The side's input and output GSG pad has been probed. The S parameters has been measured with a Rohde & Schwarz ZVA67 network analyzer. We were able to obtain a peak gain of 16.4 dB at 28.3 gigahertz, and it exhibits a steady gain roll-off at the higher frequencies. Due to this gain profile, our first 3 dB band exists from 23.7 to 39.2 gigahertz. But as we still have adequate matching and adequate gain flatness, we've decided to incorporate a second 3 dB band from 39.2 to 60 gigahertz. So to realize a combined gain bandwidth from 23.7 gigahertz all the way up to 60 gigahertz. Next, input matching level in blue here remain below negative 10 dB from 25.6 gigahertz all the way up to 67 gigahertz. Moreover, we define the effective bandwidth of our LNA as the intersection between the bandwidth of the gain and then the bandwidth of the input matching, such that the effective bandwidth of the LNA exists from 25.6 gigahertz limited by the SOM1 all the way up to 60 gigahertz limited by the gain of our LNA. The output matching in yellow here remain below negative 6 dB across from 20 gigahertz to 67 gigahertz. And we see this dual resonance response due to the dual resonant impedance that we have at the output of the stage 3. Finally, the S12, the reverse isolation, remained below negative 32.3 dB across the full measured spectrum. The noise figure of our LNA has been measured with Rohde & Schwarz FSB40 spectrum analyzer and a Pasternak noise source. By using a Y factor method, we were able to obtain minimum measured noise figure of 4.1 dB within our bandwidth. Here, the IIP3 of our LNA has been measured with Rohde & Schwarz ZVA67. We were able to obtain a maximum IIP3 of negative 4.8 dBm and a minimum IIP3 of negative 12 dBm within the measured bandwidth. The plots here shows the Rowlett stability test results. The plot to the left shows the K factor, and then the measured K factor in blue here remained above 1. These are supposed to be smiley faces to represent that it met the condition. Likewise for this. The measured delta factor in yellow here on the plot to the right remained below 1 and met the conditions for the Rowlett stability test conditions. As both Rowlett stability conditions has been met, our LNA is unconditionally stable across the full measured frequency spectrum. In our summary table, we compare the performances of state-of-the-art wideband designs. Our work to the far right was one of the first to implement a wideband LNA in 16 nanometer FinFET technology. Although in terms of 3 dB frequency, designed by Liang, the second column reported the widest 3 dB bandwidth, but they also report a very poor input matching level. Moreover, I like to highlight that we were able to obtain the widest effective frequency amongst designs with good input matching level, so below negative 10 dB. And in terms of peak gain, the design by Kazan reported the highest peak gain, but they also consumed much more power relative to everybody else. And in terms of noise figure, Hughes design in the middle obtained the lowest noise figure, but they also consumed a little more power than everybody else and also reported narrow bandwidth as well. In terms of power consumption, Chen's design in the third column obtained the lowest power consumption, but they also reported a very low peak gain as well. As all these LNAs shine in different areas, we use two Figure-Ameri equations to compare their performances. The first Figure-Ameri equation is the conventional wideband LNA Figure-Ameri equation, where it considers the peak gain, 3 dB bandwidth, power consumption, and noise figure. And using this first Figure-Ameri equation, we were able to obtain reasonable performance compared to the others. And the second Figure-Ameri equation considers the power, the gain, effective bandwidth, power consumption, noise figure, and we've introduced this input matching term, 1 minus SOM1, to penalize the recent prevalence of designs that kind of neglected the quality of the input matching to obtain LNAs with bigger bandwidth and higher gains. Using the second Figueroa equation, we were able to obtain very competitive state-of-the-art performances. In conclusion, we drawn out the radar chart for the design in our summary table. Our design to the bottom right in orange here. Our design is like the orange one to the bottom right here, while other designs are skewed in some way. So the red one is skewed to the top left, and then the green one is skewed to the bottom right. The blue one is trapezoidal and it's kind of missing this input matching level. Ours is the most balanced, most closely representing a pentagon. So in conclusion, the proposed dual resonance techniques, such as the interstage magnetic coupling and then the concurrent usage of resistive feedback technique and inductive degeneration technique, allowed us to extend the bandwidth of our LNA without critically sacrificing the other performance aspect of an LNA. So this approach enabled us to design a competitive wideband LNA with well-balanced performances. Here are the references that I've used for this work, and I would like to acknowledge that thanks to the Intel University Shuttle program, we were able to fabricate our chip. And thank you for your attention throughout this presentation.